Break. Up next, we're excited to have Jon Manning presenting Let's Use an Automated Theorem Prover to Verify Video Games. And he says that it's fun, and we're looking forward to hear him talk about that. Now, Jon Manning is a prolific author and game developer and currently working on an award-winning adventure game, Night in the Woods, which you may have heard of. Today, he's going to talk about using Z3 to describe and diagnose problems in an RPG. He will also unpick the jargon that surrounds this field and learn how to apply this theory to practice. So today, the presentation is pre-recorded, but we are really excited to have Jon here. He's live in Venulus. Hello, Jon. And he'd be happy to take questions from you during and also after the presentation. So feel free to get in contact with Jon on Venulus. Look forward to your thank you.
Hi, and welcome to Let's Use an Automated Theorem Prover to Verify Video Games. I swear this is more fun than it sounds. My name is Jon Manning, and I'm a game developer at Secret Lab. I work on a game called Night in the Woods. I also work on a tool called Yarn Spinner, which is a set of tools for working with narrative and dialogue in games. So that's really cool. I also write a bunch of books. I'd like to talk to you about the robot uprising. In particular, the robot uprising of 1895. You see, about 130 years ago, a civilization created artificial intelligences. These are service robots. They were designed to be laborers, but also war machines, so in other words, very similar to our current robots. And they were all designed to network together because they got smarter the more they were networked together, which is very, very good. Until they became so networked that they became sentient, and the creators panicked and ordered them destroyed. The robots fought back, and you know how this story tends to go. They destroyed the entire civilization and destroyed their culture, ruined the planet, and then fled into deep space and killed anyone who tried to make contact with them, becoming extremely isolationist. Meanwhile, their creators became refugees, living on their ships, hating their creations, and planning on retaking their homeworld one day. Now, this is a real problem because the Reapers, who are ancient machines that invade the galaxy every 30,000 years or so, ended up teaming up with these robots, and they're wiping out all of sentient life, which is a really big problem for those of us who are organic and sentient life. Now, this whole thing, of course, culminates in a gigantic battle between the robots and the creators, and our hero ends up tipping the battle in favor of one of them who wipes out the other, destroying an entire species. And the victor agrees to help our hero defeat the Reapers. It's a very, very sad moment. Now, this might surprise you, but none of this actually happened. This is science fiction. This is actually the plot of Mass Effect 3, which is a science fiction game released in 2012 by BioWare. In that story, roughly set around 2257, our hero meets a young creator named Tali, and she's looking for intel that'll help her defeat the robots. And our hero is interested in doing this because the robots have re-emerged, they're attacking human worlds. Unfortunately, after helping out our hero, Tali gets put on trial for treason. Before the verdict gets handed down, Tali and our hero end up trying to rescue her father. They find him dead, unfortunately, and they also find out that he was conducting extremely unethical experiments on the robots, making them fully sentient and then using them in weapons tests. This is evidence that will happen to exonerate Tali, but it will also destroy the good name of her father. There are some other ways that our hero can show that Tali is innocent. We can make a rousing speech about her loyalty, but doing that requires doing lots and lots of work to improve their charisma levels to be able to deliver that speech. Alternatively, if certain characters from the game are present in the crowd, then our hero can turn to them, but that only happens if you've made certain other choices to ensure their survival. Meanwhile, our hero also discovers a robot named Legion. Legion has slowly grown more enamored with the idea that the robots should be seen as an equal race, equal with the other species in the galaxy. And we discover that there's actually a chance that maybe these can not just be all murder bots, they just want to exist, they just want to be free. However, there's a faction of the robots who have teamed up with the big baddies of the story who just want to kill all life, and Legion is trying to stop this faction. Tali and Legion end up in a serious fight aboard the player's ship because they hate each other, especially if the player presented that evidence about the unethical experiments on the robots. But if the player plays their cards right, then we can mediate between the two. This is the end of a long story. This is the third game in a series of games, and we've spent a long time with these two species. This game's story is about endings, and the game is designed to make you pick between the end of one of these two species. Either the robots destroy the creators, or the creators destroy the robots. So we either end up with that situation, or this situation, neither of which is good. And there's a big, complex web of relationships between these different characters, between these two civilizations, that you, the character, are trying to mediate between. But is there a way to find peace between these two groups? Yep. The goal of uniting these two races is simple enough. The creators want their homeworld back, and the robots want to live. So you'll need to find someone on either side to represent you. That's Legion and Tali. And also you need to lay a huge amount of groundwork to build trust between the robots and the creators. So here's how to save two sentient species in 6 easy steps. Befriend a creator who's on a quest for vengeance. Rescue a robot on the verge of sentience. When they end up fighting over a shared history of unspeakable atrocities, patch things up. Do lots and lots of work to build trust between these two species. Make sure neither of them die in the middle of all of this. And then finally, when the two species come to blows, step in and use the support of both these two people to broker peace. Simple. So if you do lots and lots of very specific things in this game, you can end up with this ending. It requires lots and lots of extremely specific actions. So, in practical terms, what must be done in this game in order to save both species? The two characters, Legion and Tali, must both be alive. The hero must have enough reputation points, either in Paragon or Renegade. A specific mission must have been completed. And at least 5 points from the following. So there's a big long list of things that the player can do. Not all of them must be done, but enough of them must be done. And these are all actions that help build trust between the robots and the creators over the course of the story. One of them is that Tali is not found guilty of treason, and also the evidence about the unethical experiments is not released. But we also have things like the player helped Legion destroy the faction of the robots that's trying to ally with the big baddies. The player found a way to find peace between Tali and Legion when they end up fighting. We attempt to rescue an admiral who might be able to convince the rest of the fleet to not blow the robots out of the sky. And also, an additional point, if you succeed. On the point of rescuing Tali from being convicted of treason, there's a few different ways that can go. Because the player can reveal evidence about Tali's father's experiments, but doing so will enrage the robots and Tali. The player can say that they didn't actually find any evidence, but that'll result in Tali being convicted. They can give a rousing speech about her loyalty, or they can turn to allies. And all of these depend on lots and lots of other factors. So there's lots and lots of factors involved here, and with so many threads, it's really easy to accidentally design this so that several requirements conflict with each other. So is it possible to prove that we can do all of these things at the same time? We absolutely can, using propositional logic. We can construct a sentence in logical notation that describes the actual decision process. So a quick crash course in propositional logic. In propositional logic, we create sentences of terms that are combined with operators. Each sentence resolves to either a true or a false result. And these operators are things like and, or, not, equivalence, and implies, along with a couple of more esoteric operators. If you've written code before, lots of these will be fairly familiar to you, and, or, not, that kind of stuff. So the and operator, true when both operands are true, false otherwise. The or operator, true when either or both of the operands are true, false otherwise. This is an inclusive or, so it isn't an exclusive one or the other, but not both. This is a one or the other or both. The not operator, which is the logical opposite of its argument. The equivalence operator, which means the left-hand operand is the same as the right-hand operand. And the implies operator, which kind of means necessary but not sufficient. If the left-hand operand is true, then the right hand is also true, but not necessarily the other way around. So given A implies B, if A is true, B must be true, but if A is false, B is true or false. It's actually not defined. So unlike the previous operators, there's no implied truth value here, just a relationship. So here's a couple of sentences in this propositional logic notation. If the game is over, it implies that the robots are alive or the creators are alive. And it is not the case that the robots are alive and the creators are alive. So that's two separate sentences here in propositional logic. Now, on its own, a sentence is always valid. It'll always resolve in either true or false. Things get more complicated when we start thinking about multiple sentences at the same time. To take an example, can all four of these sentences be true at the same time? The game is over implies robots are alive or creators are alive. It is not the case that the robots are alive and creators are alive. Game is over is true, robots are alive is true. Can all four of those be mutually true at the same time? Yes, they can be. All four of these sentences are what we call satisfiable, so they don't conflict with each other. But what about if we assert that they're both alive? So we now say robots are alive and creators are alive. Well, that's not satisfiable because the second sentence conflicts with the fourth and the fifth. There's no way that these sentences can all be true at the same time. What if we leave all the terms undefined and just include the relations? So we're just saying, here are the relationships, we aren't assigning a specific truth value to any of these terms. This is also still satisfiable because satisfiability doesn't mean that we have a value for the variables. It means there exists at least one value for the variables such that all the sentences are true. So back to our larger problem. What kinds of sentences in propositional logic are involved here? There are lots. Here's a few of them. The code that I wrote for this presentation has 74 of them, and that's just for this part of the story. There's probably at least 1,000 needed to completely describe the entire game story, but here's an example of some of them. So we now have two questions that we want to resolve here. We first want to figure out if we've not made a mistake in the design of our propositional logic. That is, are all of those 74 constraints able to be satisfied at the same time? We also want to find what are the possible values for those terms. So that's a lot of work. We could do this by hand. In fact, before the invention of computer automated logical reasoning, we always did it by hand. But is there a way that we can ask the computer to do this? Yes, it's called with Z3. Z3 is a satisfiability modulo theory solver written by Microsoft, released as open source under the MIT license. It's written in C++, but has a very, very convenient Python library that I'll be using here today. So a theorem prover is a program that takes a logical formula and tells you if that formula is satisfiable or not satisfiable. If it is satisfiable, it can produce a model. A model is a mapping of all of the variables to specific values. If the formula is unsatisfiable, it can produce a proof of unsatisfiability. It can tell you why it's not satisfiable. Z3 can work with a bunch of different values. Most useful for us today are going to be booleans and integers, and a variety of operators are involved in those. Z3 is used in industry a lot. It's used in formal program verification, test case generation, model checking, and also the solving of constraint layouts. So here's an example of Z3 in action. We import Z3, we create a Z3 solver, we declare two variables, P and Q, and we say that they're both booleans, and then we add to the solver a couple of constraints. We say P implies Q, and P is equal to true. So we're just describing these constraints into the solver. Next we say check. This is going to check to see if all these things are satisfiable. This will actually return a value saying either sat or unsat, satisfiable or unsatisfiable. If it is satisfiable, then we can print the model and get information about the value of each of these variables that it computed. So in this case, we get P is true and Q is true because P implies Q and P is true. So here's our plan for solving our story problem about the robots and the creators. We determine all the variables at play. We determine the way that all these variables relate to each other. We determine if that complete formula is satisfiable, and if it's not, then we have made some kind of mistake in our formulation, or the problem is actually not resolvable. That's unlikely because this game has been out for about a decade now, and people would have found out. And then finally, we assert our constraints, we check satisfiability, and we get a model, and that'll tell us what must be done in order to save the robots and the creators. Here are the variables involved. Note that this is not complete. Several of these have their own dependencies. In particular, these ones represent a larger set of decisions that must be made both in the current game that we're discussing and its prequel. These actually represent a much larger set of decisions that have a very complex set of rules themselves. This is a problem roughly the same size as the one we're looking at right now, so I'll just skip it in the interest of brevity and represent it as they survived, yes or no. Anonymous user on Imager who created this graph, thank you very much. So we start by declaring all of the variables. Here we are in Python. We are declaring all the integer variables, the Boolean variables. Each one of these represents a fact about the world. We are not defining whether they're true or not. We're just defining that these are facts that can be true or false, or in the case of these first two at the top there, they're integers. Next, we add a whole bunch of relationships between these different variables. We're not asserting any particular truth value about them yet, but we are stating relationships, like if the treason trial is complete, then Tali has either been exiled or exonerated. If Tali has been exiled, it means that Shepard lied about the evidence that was found, all kinds of stuff. Shepard, of course, being our hero. One very important constraint is where we say that the ability to let the robots and the creators both live is equal to that enormous collection of constraints. So to go through these, first of all, we assert that Tali and Legion are both present. We assert that the player has enough points in either Renegade personality or Paragon personality. We have completed a certain mission. And finally, all of the points add up to at least 5. So if we have destroyed the heretic robots, that's 2 points. If we have exonerated Tali and also not revealed the evidence of the experiments on the robots, that's 2 points. If we brokered peace between Tali and Legion when they fought, that's 1 point. If we attempted to rescue the Admiral, that's 1 point. And finally, if we succeeded in rescuing the Admiral, that's 1 point. Finally, we compare that to number 5. And if that all passes, then we can attempt to make peace between these two species. To get the result, we then ask the solver, check for me, and we get back a result of either unsat or sat. If it's unsat, then the constraints are unsatisfiable and there's no solution. Otherwise, we can ask the solver for a model and through the model, get the individual values. And here's the result of one such model. So this is essentially random, but it is consistent with the constraints that we set up. What we've got here is a game state that is consistent with a potential run through the game. So here's one particular zoom in on some of these variables here. In this case, Tali was exiled, and as a result, Shepard lied about there being no evidence, and as a result, completed the treason trial mission is complete. So these things are related and are interdependent, and it's not inconsistent with one another, which is very, very important, and that's a complete solution to this setup here. But what if we want to also assert that our hero succeeds in uniting these two species? Well, we can add an additional constraint. We can say check with this constraint involved here. We add the assertion that the value of robots and creators are united is true. Now this is on top of the fact that the variable is also equal to a larger expression, the one that we saw earlier. So if that is true, if the variable is true, then in order for the rest of the constraints to be consistent, then a bunch of other things must also be true. If that turns out to be unsatisfiable, then what we've found is that it's not possible for that sentence to be true in conjunction with our existing constraints. In other words, we have demonstrated that the player could never reach this goal. And so when we get that model, we get a very different set of results. Lots more tick boxes here, lots of green check marks, because they form part of the necessary conditions leading up to the Geth and the Quarians, that is, the robots and the creators, are united. In this case, the path that the solver found was actually quite interesting. The scenario that it found involved Tali actually losing her trial. That's the Tali was exiled variable at the bottom there. But the only way for that to happen is for our hero to not reveal evidence of the experiments, which means that everything else can happen smoothly. So just to zoom in on some fairly pertinent stuff, it found all of the required things to pass and enough of the optional things to pass for us to be able to come to that conclusion. Interestingly, we actually can find ways in which the entire thing does become unsatisfiable. So if we assert that the robots and the creators unite and that evidence of the experiments was released, which is evidence that exonerates Tali but also destroys the name of her late father and enrages the robots, we run that through the solver and we get this. Z3 will result that it's unsatisfiable. There's no way for the sentences, the robots and the creators are united and evidence was revealed, are true at the same time. Now, it's often a little bit dissatisfying to just get unsat, because we want to get more information about that. If we get an unsat result, it means that there was some conflict between the constraints, but we've got dozens and dozens of constraints. Which ones are in conflict? So to answer that question, we can ask Z3 to produce an unsat core. An unsat core, also known as just a core, is the minimal set of constraints that are in conflict. This is very useful for describing and explaining an unsat outcome, and also for troubleshooting as well. So let's ask Z3 to produce the core, and for the purposes of making it look a bit nicer in these slides, I've also asked Z3 to simplify the expressions, which means it'll remove elements like equals true at the end of it, because that's redundant, and also splitting it back out into multiple statements. When we run this code, we actually get this. It's a much smaller set of constraints in conflict. So Z3's explanation is it's not possible to both broker a peace between Tali and Legion when they fight, and also to have revealed the experiment evidence. So we can tune this as much as we like. If we assert facts like Tali was exonerated because we found allies in the crowd and then run the solver, it'll deduce that those allies in the crowd are there because they survived previous missions, and the solver will just find the way that that can happen. And the outcome is, hooray! We have two sentient species surviving. Now, this is not just good for verifying that a story is complete and correct. It is also good for romance. So, let's talk about Dragon Age Inquisition. This is by the same studio, BioWare. It is a fantasy game. In this game, the Inquisitor is the player character. The Inquisitor is the sole survivor of a huge disaster that kicks off a war between magic users and the religious army that is trying to keep them from killing everyone, either by mistake or on purpose. Over the course of this game, the Inquisitor finds companions who join them to help resolve this problem and push the story forward, and they all work with you to help do all kinds of stuff. We have characters like Iron Bull. Iron Bull is a mercenary who immediately informs you that he's in fact a spy, but he'd like to work with you anyway, and he's a good-humoured, like Viking type character who likes to party and kill dragons. Solus, who is a mysterious and very, very bold elven mage who's broken the law. He's on the run from the religious cops. He's expert on magic, and he's also a bit of a jerk, and that guy who's always in your DMs. Now, over the course of that game, you will end up taking actions that result in approval changes. And so you'll actually get to see on screen, Solus approves, Iron Bull slightly disapproves, that kind of stuff. The game will tell you about the impact that your decisions are having on other characters' opinion of you. This is the good and open and honest communication that I'm in favor of. Now, an approval rating high enough actually means you can romance them. You can build a much more closer relationship with them. So the game is actually tracking these with points, which means that we get to quantify human feelings. So different actions that you take result in different outcomes. Each character has a different approval rating, and if they greatly approve, that means it's 25 points. If they just approve, that's 5, and if they slightly approve, that's 1. And the same thing, but in reverse for disapproval. Now, the game is called Dragon Age Inquisition, and you are the Inquisitor, and as part of your role as the Inquisitor, you get to sit in judgment of people and decide on their fate. And these fates can range from send them to the gallows to you work for me now, and all kinds of stuff in between. So one case is Magister Geryon Alexius. He's been captured by the player, and he's being judged for his crimes of apostasy, attempted enslavement, and attempted assassination. He's basically a mage who goes rogue and tries to kill you. There's a few different things you can do with this guy. You can have him executed, you can send him to the dungeons, you can force him to work for the library because he's quite smart, you can have him made tranquil, effectively basically destroying his mind and rendering him not a threat, or you can force him to research a particular thing. Each one of these outcomes results in a different result for different characters. So for example, if you imprison him, then Iron Bull will approve, but Cole, a different character, will disapprove. Now we can model this in a very similar way to how we model the Mass Effect problem. We can set up constraints and ensure that they're satisfiable, but there's an additional kind of data being used here, and that is the approval ratings. These are integers, and Z3 can use these as well. Integers can participate in expressions, so one such relation that they can work with in the expressions is the if relation. So the value of some integer a is x if true, b if false. So we can actually work with numbers which are unbounded type. Unlike booleans, which can only be true or false, numbers can be an infinite number of different results. Now because we can work with numbers, we can work on optimizing those numbers. So imagine that we're selling swords to passing adventurers. The higher the price, the more money we make per sale, but also the fewer that we sell. What price should we set to maximize our revenue? Here's how we can model this problem. So let's define three variables, our price, our sales, and our revenue. In this case, real is like a floating point number in this case. We can create an optimizer object. It's like our solver, but it can also do optimization problems. And we can add some relationships. We can say, here's the relationship between sales and price. That is, the higher the price, the fewer the sales. We can set a minimum amount on price, and let's also specify that our revenue is equal to our sales times our price. And we'll tell the optimizer, I want you to maximize revenue. What values for all of these variables can be adjusted such that revenue is at its highest? So if we run this, then our model will now go, yes, here's a result. If we set price to 13.5 gold pieces, then our sales will be 23, and we'll make 310.5 gold pieces. So that's an example of using Z3 in an optimization capacity. We can model the question of approval ratings in a similar way. So if we have a Boolean value, Garyon imprisoned, that's a Boolean, yes or no, and we have a couple of approval rating variables, so Iron Bull's approval rating, Cole's approval rating, and we say Iron Bull is happy when Garyon is imprisoned and Cole is unhappy if he's imprisoned, then we can build up an entire chain of constraints very similarly to how we answered our science fiction question. So to model this, I wrote a big long list of variables. Here are all the variables that are relevant to this part of the game. As before, the game is actually much larger than just this, but you know, I only have so much time here today. So our approval ratings are integers, and the conditions that certain judgments depend upon are in booleans. So certain judgments can only be made based on other parts of the game. So for example, you can only make Garyon Alexius tranquil if the player is a mage. And then we set up all of the relationships between these different variables. So I end up writing a helper function to generate each set of constraints because there's just a lot of them. But this gives you an idea of what's involved. So for example, if we decide to imprison Knight Captain Denham, then Solus, Iron Bull, and Varric will slightly approve, for example. Then we can simply ask our optimizer to maximize the value of one of these integers. So if we tell it, maximize the value of the Iron Bull variable, then it will give us a very, very high number for Iron Bull's approval rating. And it'll also solve for all of the other variables as well, telling us which decision should be made, as well as all of the dependent flags that must be set in order for those decisions to be made as well. So you can see, for example, in this case, we actually made Garyon Alexius tranquil, and as a result, we had to be a mage, and that's one of the things that makes Iron Bull very happy. We can do it for other characters as well, so if we try and optimize for Cassandra's happiness rating, that's a different character as well, then we can get the highest value we can for that. Cassandra is actually quite difficult to please with this kind of stuff. We can also minimize a target value as well. So up until now, we've been talking about maximizing a value. Let's talk about minimizing one. Or, how can I make Solus as unhappy as possible? So Solus is one of the more judgmental companions. He's a very much holier than thou kind of person. He likes to explain everything that you already know back at you, which is often fine, but like if he explains history of the elves to you, an elf, then that's quite annoying. He also has a general, very punchable face. In fact, he has a face so punchable that in one of the downloadable content packs that the game developers released, you actually can punch him. So, how can we minimize Solus's happiness? Well, if we tell the optimizer to minimize Solus, then we actually get a very, very low rating for his happiness level. But we can also note that Iron Bull's rating was quite high as a result of this. So what happens if we try to optimize it such that we minimize Solus's enjoyment of the story and maximize Iron Bull's? So we actually do both. We can provide two directives to the optimizer and tell it to solve. And when we do this, we actually get the same approval rating for Iron Bull as if we were only optimizing for Iron Bull, which implies that Iron Bull really quite enjoys Solus not having a great time. So what can we do with these kinds of techniques? What practical benefits can we use to find actual real-world problems? So Z3 is extremely useful. We can use it as a constraint solver, as an optimizer, as we've seen. We can also use it as a validity checker. Previously, we saw that there are certain outcomes that are unsatisfiable. Now, that can be really directly useful for people designing interconnected systems. To go back to Mass Effect 3, Mass Effect 3 was fully voice acted in 2 genders and translated into 7 languages. And what that means is each line got recorded 14 times. So you want to really make sure that every line is therefore reachable. And the nerds, when the game came out, dug into it and in fact found content that was not reachable as a result of bugs in the scripting language used to control the dialogue. They found that a certain character had lines that would never, ever, ever be run because of a defect in the way that the scripting system was put together. So this is an example of content that would have shown up had we tried to solve for a certain outcome. A constraint solver would have reported an unsat condition. And so you can use this to find problems or holes in your content. There's also other uses outside of the world of games. So, for example, PyXZ3 is an example of a tool that does symbolic execution of Python programs. And what that means is it runs the program offline, proving the behavior of the program without necessarily actually running it, giving you certain information about certain behaviors of that script. Microsoft, who are the developers of Z3, also use it for a lot of different purposes inside their Azure cloud platform tool. So for example, they use it for checking to see if certain firewall rules don't result in behaviors that they don't want to see. For example, connections being blocked when they shouldn't be, or connections being let through when they shouldn't be. So highly recommend that you check out this article here. Finally, Eric Pony has done a really good tutorial on how to use Z3 Pi. It's really good. I strongly recommend that you check that out. So for more information on me, I'm on Twitter. I'm Displacer. You can find my studio, The Secret Lab, on Twitter also, and you can find us on the web at secretlab.games. Z3 itself can be found on GitHub at github.com/Z3prover/Z3. Massive thanks to Claire Manning and Tim Nugent for their help with the lore of Dragon Age and Mass Effect. And thank you all so much for watching this, and I hope you have a great conference.